going to talk about what calculus really is. Calculus means different things to different disciplines. In physics, we use calculus in one very specific way, actually in quite a number of different ways. In business applications, they use different formulas, but the calculus behind it, the very fundamentals of what calculus really is the same, whether we're talking economics or physics. So what I want you to do is pause the video, because this is one of your questions, and write down what do you think calculus is. Use complete sentences. Complete sentences have a capital letter and a period, you remember. And just tell me what you think calculus really is. Did you get it? Now we're going to look at some examples. What you did in pre-cal, you did all this in pre-cal. You found, a lot of stuff with circles. You found the curvature, you found points on a circle. In calculus, and what we're going to call differential calculus, because there are really two forms of calculus that we're going to look at, differential and integral calculus. In differential calculus, you're going to look at the curvature of any arbitrary curve. Now, we can predict very nicely what happens on circles and very specific curves. But in calculus, we can use any curve, and we can find the curvature of any curve at any point, as long as it's defined. In pre-cal, you found the height of a curve at a given point. But in calculus, you're going to find the maximum height on a curve. And the maximum value, of course, is going to be given by different formula. Without calculus, you were able to find the tangent plane to a sphere is a very regular object. But in differential calculus, you're going to be able to find this plane to any surface. Now, we're not actually going to do this class, but you can. What you did without calculus is find motion along a line. And you will do this in physics. You will do this in, especially APB, a lot. While in differential calculus, you're going to find the motion along a curve at a point. And when we do parametrics, you'll do this, and you're actually going to have quite a bit of fun with it. Now, without calculus, you could find the value at any point. Now, here's the difference in calculus and differential calculus when we talk about curves. In curves, in differential calculus, we're always going to talk about the limit as f of x as x approaches c. You see, in this example, the function is, you're going to learn this is continuous and actually differentiable at every point. Well, here, the function is not actually defined at this point, but you can find the limit. What happens as you get really, really close to that point? Now, without calculus, you can find slopes of lines very easily. Slope, m, is a change in y over a change in x, rise over run, you've done that. But in differential calculus, you're going to find the slope at a given point, at a tangent to a curve. Now, without calculus, you find the secant line to a curve, which is basically finding the slope between 2 points on the curve. While with differential calculus, you're going to be able to find the tangent at any point, as long as it exists. Now, without calculus, you can find the average rate of change between time A and time B. While with differential calculus, you can find the instantaneous rate of change. This is, for example, finding the average speed you travel getting to work or to school. While this would be instantaneous. This is what the police officer gets you with when he looks at your speedometer. He goes, your instantaneous rate of speed was 75, and the speed limit was only 55. So this has a lot of applications. Now, you'll notice up here we have the symbol here. So this needs to go into your notebook. Read the problem and answer the question in your notebook. Did you get it? Okay. What about this problem? This is problem 2. Let me put my pen on. Okay, did you get it? Now, in calculus, the first part we're going to cover is really what we call the tangent line problem. If the curve is something nice that we're really familiar with, it's easy to find the tangent line, especially if it's, a straight line. But a lot of times when we have this function, y is f of x, it's really hard to find the tangent at any one point. Now, one thing we do for the tangent line formula is we find the secant line. And with the secant line, you can find the slope of the line between any 2 points. And of course, once you have the slope at a particular point P, you can find the equation of a line. Now, what happens as we adjust that point? Suppose we go from here to here. That's a different secant line. And what if we go from here to this point right here? Do you see the slope of these lines is getting closer and closer to what the slope of the tangent line is going to be? So here's a problem for you. Graph this equation, 4x minus x squared, and the point 1, 3. Now for points, q, x, f of x, for x is 2, 1.5, and 1.1, those are your x values. Find your values. Find the slope of each secant line. Use your slope results to estimate the slope at 1, 3, and describe how you could prove your approximation. So this is really one problem. One, but it's A, B, C, D, D, and E. Pause the video until you're done. Now there's another part of calculus we deal with, and it's called integral calculus. Differential calculus is slopes of lines. Integral calculus is areas. Now you can all find the area of a rectangle, length times width. But with integral calculus, you're going to be able to find the area under curves, when this is not necessarily something nice and easy to figure. You can find the work done by a constant force. You know that work is FD. If you haven't taken physics, then you will. And this is a very straightforward formula. But with integral calculus, you can find the work done by a variable force. Now, if you're in AP Physics B, what you're going to find is we're going to tell you what the work is for like a spring or other variable forces. But with integral calculus, you don't have to be told that. You just know it. You can figure it out. Now, without calculus, you can find the center of a rectangle. Okay, do the corner to corners there. With integral calculus, you can find centroids of a region. This is really, really cool stuff. We're not going to cover it this year, but it's really, really cool stuff. Now, without calculus, you find the length of a line segment, and not just by line your ruler down and figuring it out either. But with integral calculus, you're going to be able to find the arc length, all right? How long is any curve, no matter how funky it is, you're going to be able to find it. Now, without calculus, you can find the surface area of a cylinder, while with integral calculus, you can find the surface area of what we're going to call a solid of revolution. You're going to have a lot of fun when we do these. Basically, we take a curve and then we rotate it around the axis. I know that sounds kind of scary right now, but it's really, really fun. Without calculus, you can find the mass of a solid of constant density, because you know the density is mass per unit volume. So the mass is, of course, the volume times the density. But if you have a variable density, life gets a little bit more challenging. Without calculus, you can find the volume of some rectangular solid, where volume is length times width times height. But with calculus, you can find the volume under a surface. All right, kind of cool stuff. Without calculus, you can find the finite sum of a number of terms. Now, it may be a royal pain. You may have 150,000 of these, but a finite number, you can add them up. But with integral calculus, you're going to be able to find the sum of an infinite number of terms. All right? So there's a lot we can do in calculus. Integral calculus is basically an area problem. Suppose I have some funky curve, y is f of x, and it doesn't matter what f of x is. What is the area between A and B of this curve? That's what we're answering. There are so many reasons you would need to know this. And as the course goes on, you're going to have the opportunity to explore those. Now, one of the easiest ways to do this is to use rectangles. Suppose I have some funky curve. I can I can start at A, and I can go up to the curve and make a rectangle. Now, rectangles are easy because the area of a rectangle is base times height, where the base is this distance right here, and the height is from this line all the way up, and this is actually the value of the function at this point. But you see over here, the value of this function is not equal to the height anymore. All right, so you find the height at this point right here, and that is the height for your entire rectangle. Now you can see we're missing parts. Can you see that? Let me change pen color here. This part right here is missing. Come on. This part right here is missing. Okay, this part right here is actually overshooting, while these two are undershooting. Now, if we increase the number of rectangles, I don't know if you can't really see it on this one, but it turns out that the parts you're missing over and under actually decrease, and this is a huge hunk of integral calculus. Now, try this, where you're going to use the rectangles to approximate the area of the region bounded by y equals 5 over x. And you're going to go from y equals 0, which is this line right here, y equals 0, x equal 1, whoa, not a good line, to x equal 5. So basically what I want you to do is to write the area for each rectangle and add them. And when you're done with that for both of these, come and answer the question B. Describe how you could continue this process to obtain more accurate approximations. And remember, use complete sentences, P-L-E-T-E. My pen is not working. It's giving me grief. Sorry about that. Complete sentences. When you're done, turn off the tape and finish the rest of your homework.